Okay, we are very happy to have Yusheng from Boston University, Boston College, to give us a talk. And his title is Generalized Theta Correspondence between double covers of orthogonal groups. Yes, please.
Okay, thank you. Thank you very much for the invitation. It's always very good to be back to US, although it's virtually, but it's very exciting. All right, so I'll go ahead with the title of the talk, theta liftings on double covers of orthogonal groups. So start by overview of the talk. First, I'll give a brief and informal review of this classical global theta correspondence. And then I'll try to generalize this correspondence to other groups. So I will try to set up this step by step. So I'll introduce metaplectic covers and how to define a generalized theta representations. And then, of course, there's some necessary tools for us to define this correspondence. And then I will give the global statements and a sketch of the proof. All right, and most of the things here are going to be global contents, although I want to make a remark at the end that some like parallel statements in the local settings can also be made. All right, so let me just proceed to the first part. So since we are mostly working on the global case, let F be a number field and with its ring of the delts. And if you fix a non-trivial additive character, then say psi, then you can attach to it a theta representation that's denoted by big theta on say the metaplectic cover P4 and K. And then also if you have a pi, which is a classical automorphic representation of a symplectic group SP2N, then of course you can show that the product of this dual pair is split in this cover. So in other words, you can view this theta representation as a representation on this dual pair, so that you can consider this integral pairing with any functions in pi and any theta function theta integrated over this symplectic group to get a function on automorphic functions on the even special orthogonal group. All right. So in other words, this will give you a theta liftings from the symplectic group to the orthogonal groups. And if you, of course, I want to mention that this is basically the notation for the talk for the daily point of the group modeled by the discrete points. All right. So if you allow like various input data of phi and the thetas, of course, this will generate an automorphic representation of the even orthogonal group. So this is the very classical theory, and of course there are many things that one can study and talk about. In our interest, we will be focusing on one aspect, which is the Rallis tower. So meaning that you fix the representation pi and varying the rank of the rank k, then you obtain a tower of theta liftings to the orthogonal group SO2k, and of course with different k's. I think Rallis showed that there is a non-zero lifting somewhere around this tower for a particular one. And the first non-zero occurrence that's denoted by FO pi is always cuspidal. And towards this direction, I think that more things can be done. So Ginsberg and Grivich is the first ones to show that, maybe the first few to show that you can try to parameterize this first occurrence by the wavefront sets of the representation pi. All right, so they have these like very precise statements that says that if pi is a representation, cuspidal representation of a symplectic group SP2N, and suppose that pi has a non-trivial Fourier coefficient corresponding to the unipotent orbits, which is given in terms of partitions of integer 2n. So suppose it's given by this partition 2n1 to the power like r1 of 2n1s and until like rp of 2np's. Then if you denote the length of the partition by the number of integers appeared in this partition, which is the sum over ri's, then the conclusion is pi has a non-trivial lift to the orthogonal group SO2n plus 2l. All right. So a direct consequence is that if the wavefront set of pi contains such an orbit O, then this was says that the first occurrence, if you indicate this by the rank of the group that it leads to, is going to be at most n plus L. All right, so this is like the motivation of our problem today. So suppose now we want to study like a possible generalized theta correspondence to say other groups. Then maybe the first ingredient that one should think about is the theta representation, which is used as the kernel functions in the integral pairing. So the theta representation, the global theta representation, I think it was first pointed out by Kastan that is a minimal representation, and which is the key property that makes this correspondence work. So so that means if we can, construct a similar representations for other groups that has like this kind of minimality properties, then maybe we can hope that we can construct a theta correspondence for a new dual pairs. All right. So this global theta representation classically was, I think, constructed by using the wave representations. Of course, it can also be constructed by residuals of certain Borel-Eisenstein series. So this is like a more general way of constructing it. So that means if we go with another group, this will be the way for us to construct similar objects like this.
Yusheng, could I just clarify? So I guess the wave representation, it cannot be totally constructed by residues of Borel-Eisenstein series, right?
Yeah.
I mean, a piece of it can be, but
yeah, that's right. Yeah.
Yeah. I mean,
so
okay.
Yeah. So it's just like the philosophy is like trying to like construct similar objects like on covers. So you can use this kind of construction, which is like quite a general way. I think Fangao has like a well-written survey on this topic. So I'm going basically, a routine walkthrough of what he has done in the paper. All right. So let me first talk about the metaplectic covers. So I want to be quite general for this one. So F is a number field that contains enough roots of unity, say UR, which is the group of all other roots of unity. And let A be the ring of delts. So G is some split linear algebraic group of F. And we denote this G2.R over a delts with the metaplectic R-fold cover of G over the delts. So this is going to be a topological central extension of GA by the roots of unity, which satisfies this solid sequence. Okay, and I'm going to be very in a classical way of describing it in terms of the second second cohomology group. So in other words, like if you are given if you're given two co-cycles in this second cohomology group where the roots of unity here is considered as a trivial G module, then this will give you a corresponding cover, and the equivalent covers will be described by just two co-cycles up to some co-boundaries. All right. So in order for us to understand this cover, it suffices for us to understand the split torus, the pullback of the split torus and the unipotent element, unipotent subgroups. Since we know that for this kind of construction, the any unipotent subgroups is splitting canonically in the cover. So we just need to understand the pullback of the maximum split torus in order for us to understand the cover. And the unfortunate thing is the pullback is in general not an abelian group anymore. But the lucky thing is it's not too far away from being abelian. So it is a generalized Heisenberg group. So for this kind of group, this any genuine representation of the pullback of the torus is uniquely determined by a genuine characters of its center. So here for a genuine representation, what I mean is the roots of unity in the cover actually acts non-trivially. So once you fix the embedding of the roots of unity inside the complex numbers, then it basically acts by the embedding. Okay. Now by this Neumann theorem, so any generic representation of the pullback of the torus is determined by some central characters. So if we start by a character of the split torus, which can be parameterized by some multi-complex variable s, and then you can let chi s be this generic characters from the center, such that if you pre-compose it with the projection map, it will recover to the characters that we fixed at the beginning for the split torus. And then by the correspondence, there should be a representation of the pullback of the torus T tilde, which we denote by I chi s. All right. So of course, you can allow the splitting unipotent radical of the Borels to act trivially on this representation, so that it can be regarded as a representation of the pullback of the Borel in the standard Borel. And then one can construct this parabolic induction of the representation I chi s, of course normalized by this modular characters of the Borel. And with this, you can pick a section over the complex variables and construct the Eisenstein series attached to it. So this is the construction of the Eisenstein series. So usually it will be convergent in a cone-shaped region, and it has like metamorphic continuation to all the compressed variable s. All right, and it all has holes at certain exceptional points. So basically, those points where the characters will be like almost trivial, as trivial as possible. Like I will not give you like the specific description of it, but what we can do is we can actually pick a specific choice of such exceptional points, and then form the residual representation of this Eisenstein series at that point. And this is what we call the theta representation of the cover on G tilde, the alpha cover G tilde over the delts. Okay. So here are some like no examples. So this, not all of them, but just what I want to include something, some of the examples that are very important. So I think the first case I think starts from Kastan and Patterson in '84. They did this for any arbitrary powers. Maybe I should say, I mean, like if I equal to 1, this is the usual linear group. So I just put it up greater equal to 2 for any alpha general linear groups. And the case where we are most interested is the second one, where Friedberg and Ginsburg construct this theta representations for the special orthogonal groups. So 2n plus 1. It was constructed as the fourfold cover, but actually it behaves like a double cover. So that's why in the title I put it as double covers of orthogonal groups. And also around like the similar times, E.R. Kaplan and Spencer Leslie did the case for G spin groups and the fourfold cover of symplectic groups independently, respectively. All right. So this is the way that we construct a similar object to the classical theta global theta representation. But the downside is such a representation is only a small representation instead of a minimal representation. And to explain this, we have to use the language of unipotent orbits. So this is like a notion for like general reductive groups. But for simplicity, I will only illustrate on the group that we are interested, which is the odd special split special orthogonal groups. All right, so we take the realization by this bilinear form attached to this anti-diagonal matrix J 2n plus 1. All right, so this has the advantage that the upper triangular matrices will contain all the positive roots.
Yusheng, could I ask a question about this data representation? So am I right that they can sometimes even be generic? Meaning it has a Whittaker model? Because I seem to recall that they were.
I think they are like, I don't, maybe in the lowest rank case, but they are very small in general. Like they are opposite to the generic ones. Like the wavefront set is like very small, like instead of the.
Yeah, because I seem to recall in Kashtan-Peterson, they have some, or maybe Peterson as examples where even these theta representations could like support like Whittaker.
I don't think so, unless like the rank is like small enough that the what's it called, the unipotent
I
orbits
understand the small rank. Yeah, correct. I understand.
Yeah. So, but if the rank is like big, usually like arbitrarily big, I don't think this is going to be generic. This is actually going to be like totally opposite to generic. Yeah, but like not minimum one. Yeah.
I recall Yuanqing's result on the GLN case.
Yeah.
I think I have some cases is like if the cover and the rank is satisfies a certain patterns, it's going to be also generic.
Yeah, I think there are some cases depending on the degree, the interaction between the degree of the cover and the N in GLN. Under some conditions, this data seem to be can be generic.
Yeah. So sorry, I was thinking only about like the double covers. So yeah.
Oh, I see.
Like allow arbitrary covers, these things may be good. Yeah, different.
Yeah. Okay. Thank you.
Yep. All right. So let me talk about unipotent orbits. So this let's look at SO 2n plus 1. The unipotent orbits is going to be parameterized by the partition of 2n plus 1 with the condition that even integer occurs with even multiplicities. All right, so suppose say O is a unipotent orbits given by this partitions of integers, so which means P1 appears R1 times, etc. And we can associate each PI and torus, a diagonal element, which is one parameter with parameter T, such that the power of T decrease from along the diagonal, starting from Pi minus 1, decrease by 2 every time until you hit 1 minus Pi. And you collect all this kind of one parameter diagonal elements to form a torus element and try to rearrange it by some wild group elements so that the power is now increasing along the diagonal. So this will be a one parameter torus elements, and you can allow it to act on the unipotent radical of the Borel. The action is basically, if you look at any like one parameter subgroup or corresponding to some positive root, then the action is a conjugation action that raises the parameter, change the parameter from R to R multiplied by a power of T, and the filtration is going to be depending on the power of T that the action the action is. So in this way, you get a finite filtration of these unipotent radicals. And of course, you can also look at the stable, like the fixed points of this action. Look at those root group that is fixed under this action, including those negative ones. And you generate a group by this and the split torus, which will give you a Levi decomposition of a parabolic subgroup, where the corresponding Levi subgroup is this, and then the unipotent radical is the V1, which is the first degree filtration. All right. So this will give you a parabolic subgroup of SO2n plus 1. So let's go for a little bit more. So if we have the unipotent orbits O, let's just, since we fixed one, so let's just suppress the O from all the notation, denote VI for the filtrations and the M to be the Levi subgroup that we just had. And also denote Li to be the abelianization of this each of the filtration VI. So the Levi subgroup M actually acts on L2, which is the abelianization of the second filtration by conjugation. And if you look at the action over some algebraic closure F bar, this action has dense open orbits. So you can pick a representative and then look at its stabilizer under inside this Levi subgroup. Then this stabilizer will be a reductive group, although this, the actual group depends on the choice of the representative, but the Cartan type is independent of that. All right. And let's go back to the field we have. So in this, if you look at only like the action over this number field F, but now this induced one action on the character group of this abelianization. And under this, you will also have orbits, and then you look at those characters such that its connected component of the stabilizer inside the V subgroup is of the same pattern type as the one that we had earlier when you base change to the algebraic closure. So then you can basically extend this kind of character trivially to a character of V2 and call this a generic character. This don't be confused with the generic representation. But this is actually a generalization of the ideas of generic representation. All right. So just give a simple example of such a generic character. So suppose G is SO5, and the unipotent orbit is given by 3, 1, 1. So in this case, the one parameter torus element is given by this diagonal element. And in this case, the V subgroup is GL1 times SO3. And V2 in this case is itself abelian and given by this unipotent subgroup, which is essentially isomorphic to 3-dimensional space. And if you pick the representative to be U0 equal to 0, 1, 0, then the stabilizer is going to be SO2. And so if you fix a non-trivial additive character, then the generic character can be chosen to be of the form psi O, which evaluates U. If you describe U in terms of X, Y, Z, then the character basically takes value on X plus beta Z, where beta is some non-zero element. All right, so this is just some examples of generic characters. But the important thing is with this, we can define the Fourier coefficients of an automorphic representation pi, or maybe I'll discover, since everything happened here only happening in the unipotent site, which is split in the cover. So basically, there's no harm for you to generalize this to the cover of the group. All right, so suppose you have pi and you have like psi O to be a generic character associated to a unipotent orbit. Then for any automorphic functions in pi, you can define its Fourier coefficient to be given by this integral, which is integrating phi against the character psi v over the v2. Notation is maybe better to be coherent, v2, all right? And this is basically a generalization of the Whittaker coefficients in a non-generic case. As you can see that in the generic case, this is essentially equal to the Whittaker coefficients, where the generic character is just the, for example, like the Gelfand-Grave characters, etc. All right. So, and of course, we can say that the unipotent orbit O supports pi if there is some data phi and the psi O such that the integral is non-zero. Otherwise, we say that O does not support pi. All right. So with this, we can explain what the small and the minimum means in our case. So first of all, I want to say that there's an order of there's partial order relation on the set of unipotent orbits for a group. And for simplicity, we can just describe this kind of this partial order by the dominance order on their associated partitions. There's an equivalent way of defining these partial orders. So the wavefront set is given by the set of unipotent orbits such that any unipotent orbit is in this set if it supports the representation pi, and any other orbits that is bigger than it does not support it. So it's the set of maximum unipotent orbits that supports a given representation. All right. Let's go back to the classical ones. The global theta representation is minimum as the wavefront set is given by a single element set, which is the minimum unipotent orbits of the group SP4 and K. All right. But the ones that we defined for other groups are not minimum. For example, the one that's constructed by Bump, Friedberg, and Ginsburg is only the wavefront set is given by this. Depends on the parity of the rank n. Is given by this unipotent orbits on the particular partitions. And just the rank. Just to make sure that the even number occurs even with even time, so that it looks different for different parities of the rank. But you can see that for big enough ranks, this is not going to be minimum, not even next to minimum. This is going to be like small, but not like as close to the minimum extreme. All right. But the good thing is this is already enough to construct a non-minimum theta correspondence. So we will describe this. So so we have to find a dual pair. So in this case, the dual pair is going to be the even and odd orthogonal groups. So, I mean the cover of them. So I'll just say I will probably omit the cover when I was referring as the cover of the groups in the data talks. All right. So suppose pi is a genuine Caspida automorphic representation of the cover of SO2n plus 1, and theta is the theta representation of a bigger split of orthogonal group SO2n plus 2n plus 1. And you can consider this embedding of the product of these two groups inside the bigger one. Of course, you have to identify the roots of unity here. Then you can define the functions on this even orthogonal group, the cover of it, by this integral pairing similar to the classical case. All right. But there are some subtlety here I want to explain. First of all, although our things are actually coming from the cover, but I only integrate on the linear part. I mean, I use the highlighter. So the integration is done over the linear group. This is because the product of these two is not genuine in general. So if you want to produce a genuine function f for the cover, you have to only restrict to the linear group. And for this, I actually fix a section of the cover so that the discrete group SO2MF is split inside the cover, so that it makes sense to talk about a function that is invariant by the discrete points.
Yeah. So Yusheng, could I'm afraid I may have to go now, but can I just ask a question before I go, which is, so this dual pair, right? I mean, in the local setting, am I right? There were papers of Hang Yan Lok and our colleagues here, and Gordon Savin that sort of in the Archimedean case, right? I don't know, maybe they just were Archimedean case, where they sort of determine the data correspondence locally quite completely, maybe if I may say. I mean,
I think I'm not sure if like they do it like completely, but like they define such objects in the local settings.
Okay. I mean, they did prove. I don't know whether it's because they assume one of the group was compact or something, but anyway, it's too bad Hang Yan is not here. Otherwise, we just ask him. So yeah. Okay. I'm afraid I need to go now. Yeah. My wife is waiting for me. So yeah. Okay. So enjoy the rest of the talk. Okay. Yeah. Take care.
You.
Yeah. Bye-bye.
See you. All right. Should I continue? Okay. Okay, I just explained that this is going to be a function that is invariant by the discrete points, and this is split. And you can, the same story is you can generate an automorphic representation, which is new in this case for the cover of the even orthogonal groups. All right. So immediately you can think about like, is there any like Tower properties that can also exist in this case? So the answer is yes. So you can fix the representation pi and vary the degree of the M to obtain a tower of lifting to genuine representations of various SO2Ms. All right. And the first occurrence in this case is also well defined by Friedberg and Ginsberg. They actually show that the first occurrence is going to be at most 4n, which is the rank of the, which is going means that every pi will lift non-trivial to the cover of SO8n over the dells. I mean, its cover. All right, but this is quite a coarse like upper bound since it applies to all representations. If you want like specific covers for a specific representation, then you need to work harder. So for example, if pi is assumed to be generic, that's just to say that the wavefront set of pi is given by this one single partition of integer of 2n plus 1. And then they show that the conjecture that pi lifts to a generic automorphic representation of SO2n plus 4. In this case, that means the rank is n plus 2. So if this conjecture were true, then that means that this is going to be the new upper bound for a generic representation. And they actually show, conjecture actually has a second part that this lifting is going to be generic as well. right? So the conjecture has like two parts. First is a non-zero lifting to certain group, and second is you can describe the lifting by a specific wavefront set. All right, for at least for the generic case. Towards this, they prove this necessary condition for the lifting. So they prove that its pi is genuine cuspidal automorphic, not assumed to be generic at the first place, but we assume that the lifting to SO2n plus 4 is generic. Then they show that the representation pi that we start with must be generic. This is like a backward direction of the conjecture, but this is for the generic case. So we want to expand this conjecture to more like general cases, including non-generic representations. So
so the pi is you start from the pi is you already assume pi is irreducible, right?
Yes, yes.
Okay.
I mean, you mean it's irreducible? Yes. Yeah, I didn't put that in the top. Yeah.
Okay. Okay. Good.
Yeah. All right. So suppose pi is now we assume like in a more like a non-generic case, pi is supported by this wavefront set given. I mean by this unipotent orbits which consist of only odd integers. So in this case, it will be this one, and then you can define the length of partition to be the sum of the powers as well. And then we conjecture that the lifting is non-zero to SO2n plus 2L plus 2. And the wavefront set of the lifting is going to be given by this new unipotent orbits described by this partition, where basically you add 2 to each of the integers appears in the previous partition, and then attach a 1 at the back. All right. So immediately you see that if this is generic, that means you have 2n plus 1. Then according to this pattern, then you should lift to 2n plus 3 and 1, which is also generic in the lifting to SO2n plus 4. In other words, this generalization coincides with the generic case in the previous page. All right. So in general, to prove this one is not easy thing. So what we can do is actually to prove like a similar statement to their generic case, which is the backward direction. But before that, I want to point out that this conjecture also agrees with the dimension equation that was proposed by David Ginsburg. All right, so this is a notion that he introduced to give a heuristic necessary condition for the first occurrence. All right, so basically that means if you have a first occurrence to take place and you have like a description of its wavefront set, then you should get a global unipotent integral. And that means in the integral, according to him, then the dimension, the sum of the dimensions of the representations that were involved, which is in the integrand, I mean, and should be equal to the sum of the dimensions of the groups that were integrated. So in our case, the integrand consists of two thetas, which is the representation pi and the theta representation. So the sum of the dimensions should equal to the integral domain that we have. First one is integrating over the SO2n plus 1, and the other one is integrating over some unipotent subgroup, which correspond to the dimension of the theta, the lifting of the theta representation. So according to the dimension equation, if this conjecture was true, a necessary condition. So if this conjecture was true, then you should have this equality. So this is indeed the case for our conjecture. So you can so I will not show the proof here, but basically we do have this equality holds in this conjecture case. All right, so this is basically the way that one can hope to detect if a non-zero occurrence occurs for certain kind of liftings. All right. So let me go back. Yeah.
I mean, your last comment is this is the dimension formula agree with the conjecture. So
yeah.
I expect it's kind of like going to give you a non-vanish period integrals, right?
Yeah, that's right. So but this is only a necessary condition, which means like if that lifting is non-zero, then this must be true. Yeah, so which means you can check for that. you can check for various kind of like liftings to see if this dimension holds. If the dimension holds, that means this might be a non-zero lifting. Yeah,
I see what
or
you
not.
mean. Okay.
Yeah. So this is just like a give you evidence, like a hint of some kind of like possible results. Yeah. So so towards the conjecture that I just stated, I will state the global theorem that for the talk. So pi is irreducible. I put irreducible everywhere. Yeah. Genuine cuspidal automorphic representation of SO2n plus 1. And suppose the lifting to SO2n plus 2L plus 2 is non-zero and supported by O prime, which O prime was given in the earlier talk, earlier slide, sorry. Then pi must be supported by the unipotent orbits O. So this is basically like parallel statements to the generic case. Instead, we have like non-generic representations in our theorem. All right, so just give like a small lower rank example to illustrate the idea. So pi, suppose, is a representation of SO7 of the dells, and suppose it has a non-zero lifting to theta pi, which is a representation of automorphic representation of SO14, and the lifting is supported by this O prime given by 5 square 3 1. Then pi must be supported by this unipotent orbits given by 3 square 1. All right, so this is basically the idea of like the theorem for general other arbitrary representation that satisfy the conditions. So I want to first give you an outline of like the proof, the idea of the proof. So basically we begin with a choice of generic character associated to this O prime and some input data such that by assumption the Fourier coefficient is non-zero, since we assume that the lifting is supported by the unipotent orbits. So then we'll do Fourier expansions of the theta functions with respect to some unipotent subgroup. The problem is the unipotent subgroups in general are not abelian in general. So we have to pick the right one to do the expansion. All right, suppose we can do that, then you can express this integral in terms of sum over integral contributions of characters or with respect to that unipotent subgroup. And you show that only a small group of them give you a non-zero contribution. So all the other integrals are going to be 0. So with those surviving summands, you can continue this process until you hit an integral that contains an inner integral that's a Fourier coefficient of pi with respect to certain generic characters. So that means this integral here is going to contain an inner integral that is a Fourier coefficient of pi. Since this overall integral is assumed to be non-zero, this inner integral must be non-zero. So that is the procedure of proving. So I'm going to use the remaining time to demonstrate the proof for a lower rank case, which is the one that I just mentioned. So the lower rank case is the one that's from SO7 to SO14. So the O prime is given by 5 squared 3 1. In this case, the V2 here is given by this unipotent subgroup. So the asterisks are just to make sure that things are orthogonal. And the abelianization of V2 here is going to be coming from two parts, the X part and the Y part. So X is going to be basically isomorphic to 2 by 3 matrices, and Y is going to be isomorphic to 3 by 4 matrices. We can pick a generic character that is given by the following. So on the X part, it's very straightforward. You evaluate at the diagonal. On the Y part, you have to do some strength things that make sure that you get good characters that helps us in the end. So I define to be this one. All right. So I'll refer the character psi v in the later parts as the X part and the Y part. All right, so by our hypothesis, we can actually find some phi such that the following integral is non-zero by our assumption that the lifting is supported by a specific unipotent orbit is O prime. All right, so we can continue this, but first let me just embed the pairs of the orthogonal groups into the big one. All right, so I'm going to embed the even orthogonal groups into the four corners, and the odd orthogonal group into the center. All right. So and the first thing is to find the right unipotent radical or unipotent subgroup to do the Fourier expansion. So in this case, we use the unipotent radical of the maximum parabolic subgroup P1, which has the corresponding V subgroup given by GL2 times SO7. All right. So this is actually good enough for Fourier expansion, but actually we can actually shrink a little bit more, since you can see that the unipotent radical unipotent subgroup V actually has a non-trivial intersection with R1. So if you denote the intersection by V lower one and let the remaining part of V be the V upper one, and consider the complements of V lower ones in R1 by H1, then H1 is going to be a Heisenberg group given by matrices of the form. So this is going to be H1. This part is going to be V1, and together they now make you R1, which is the unipotent radical. All right. So the thing is, this Heisenberg group has the properties that its center, which is here, actually coincides with the center of V1, and the V1 is already integrated in the static integrals. So that means we can integrate, we can expand the static integrals with respect to characters of this abelian quotient, which is H1 modeled by its center. And for that, for every characters in this abelian quotient, its contribution is going to be by this is going to be given by this integral over the characters psi H1 over this abelian quotient, and we can always combine the integral from V lower one and the H lower one to give you an integral over R1. That means we will also have to separate the characters psi V into X part and Y parts. We keep the Y parts and combine the X parts with the psi H1 to give you a characters of psi R1. All right, so this is going to be like the contribution of characters for any character that is inside the abelian quotient. And you can allow this diagonal subgroup GL2 times SO7 to act on the character group of this quotient. In this case, you can use the Pontryagin dual to realize this quotient, the character of this abelian quotient, to be isomorphic to 2×7 matrices over the ground field. And so then you can classify all the characters of this quotient by the following types. The type 1 is those the null space are totally isotropic. So depending on the rank of the representative, you can pick the following 3 different types, different orbits. The C1, C0, C1, C2, where the rank of the matrices is 0, 1, and 2. And the remaining ones are going to be those matrices sitting inside an orbit that is represented by a matrix that contains a non-isotropic row vectors. So for this kind of characters, you can immediately show that the psi R1 is going to be a generic character associated to the unipotent orbits given by this partition 3 square 1 to 15 in SO21. And this means that this integral, that the corresponding integral contribution of this character contains a Fourier coefficient with respect to theta. And that must be 0 because the wavefront set of the theta representation is given to be 2 to the power of 10 and 1. So this is incompatible with the wavefront set, which means the Fourier coefficient must be 0. So we only need to check for type 1 orbits. For type 1 orbits, suppose the representative is given by CQ, where Q can be 0 up to 2. The integral contribution is given by the following. All right, so here, the psi R1, we have a very explicit description of it. It's going to be psi 1, which is the coming from the psi phi part, which is invariant at the diagonal U13, U24, together with the sec C1, sec CQ. All right, so sec CQ depends on the rank of the representative, can be either trivial or invariant at U18 or the sum of U18 plus U29. For this kind of contributions, we can use the technique of loop exchange to get that the contribution is equal to the integral that we recover. So we basically conjugate the variable u by these some important elements zq and some wild group elements omega q, so that we transform the characters from psi r1 back to psi 1. And the what's left is that you will have some non-trivial, you have some wild group elements and the equivalent elements that was as evidence of the conjugation. All right, and when q is 0, these two elements omega q and zq are just trivial. So this is the root exchange. The important thing is this will give us a integral that is corresponding to the character psi 1 that we need. So in this case, psi 1 is going to be evaluating as, if you look at this matrix, it's going to be evaluating at these two positions of the unipotent subgroup. And what we can do is we can further define this unipotent subgroup, which we call R2, which is like a smaller unipotent subgroup that is actually inside SO17, but you embed it into SO21. And then what one can show is that the previous integral is going to be invariant by the adelic points of this unipotent subgroup. So in other words, if you integrate over these unipotent subgroups, you will get the same integral. So what we can do is basically expand this integral domain from R1 in the previous page to R1, R2. So you get a further expansion where you get only constant term if you non-zero contribution. Now the story goes as the intersection of this new unipotent subgroup after you conjugate with this wild group element with this V upper one is non-empty, or maybe I should put non-trivial. It always contains the identity elements, but it will contains some root elements such that we call it XR, such that the psi V is going to be non-trivial at this one parameter root element psi XR. So that means this XR is going to be evaluated twice in the integral expansion, where one is with a character psi V and the other one is without a character. So a change of variable will give you that this integral is going to be 0 because you will get an inner integral that's evaluating of this non-trivial integral, which will give you 0. So this shows that all those contributions from the characters corresponding to CQ with Q less than 2 will be 0. And only Q equal to 2 will give you a non-zero contribution. So that will give you the remaining, which means that the beginning Fourier coefficient is going to be equal to the sum over this gamma, which is SO7 mod up by Q2. In other words, we pick psi C2 to be our representatives, and then you let SO7 add on these characters, and then Q2 is just the stabilizer of this action. So Q2 here is going to be the maximum parabolic subgroup SO7, where the Levy is GL2 times SO3. All right, the upper 0 here means that the GL2 factor is omitted. So in other words, Q20 is basically SO3 times U. All right, so we can combine this gamma here with the G here to rewrite the integral as SO7 modeled by Q20 over the ground field F. All right, so this will kill this basically is combine the summation with the integral. And then we go to the last step, which is to continue to expand on this new unipotent subgroup, which we call H3. Okay, so it's going, I mean, everything has been done in the outer parts here by the previous steps. What we now is going one step inside by doing expansion on this. And this part here, which I'll use a color denote, is going to be the remaining part of V, which we denoted by V upper one, after conjugate by this omega 2 that we have in the earlier stage. And together that will give you a unipotent radical, which we call R3. R3 is going to be the whole thing here. All right, similar to R1 and R2. All right, and our expansion here is again durable because the center of this H3 coincide with the center of the V upper one after the conjugation. And any character this time will give you like a contribution of the form similar to the earlier parts. The only thing is I combine those groups that were involved. So we have integrate over R1 and R2. Now we integrate over H3, which combined with V upper one will give you R3. So I combine the three integrals and combine the respective characters to be psi R. All right, and what's can be shown in this case is that the non-zero contribution will be coming from those characters that if you describe it in terms of matrices, 3x3 matrices, the row vectors of it, the first row and the last row is going to be a hyperbolic pair, and the second row is going to be a unit non-isotropic vector. So in this case, identity and matrix 3x3 identity matrix is representative, and SO3 acts on it, actually acts on the set of such matrices or such characters transitively. So we can sum over, elements in SO3F to describe that the previous integral will be equal to this sum. All right, and then the similar story is you can combine the SO3 with the G here to rewrite the integral as SO7 over the unipotent UF. All right, and this is close to the end. And since we can rewrite this integral domain by the product of the direct points over the discrete point of the unipotent radical U and some some adelic quotients. And if you can conjugate, say, n prime here, coming from here, and you can rewrite this as n prime g prime, and you can conjugate n prime to the left, and you will see that, and then you will lies inside R, the integral domain of U, and then you do a change of variables that will swallow the part of n prime. But because you have a non-trivial character evaluating at U, this will spit out the character evaluating at n prime, which is essentially psi n13 plus n24. So in other words, this above integral that will contain an inner integral that is of the form of psi ng against phi ng against the character psi un, where psi un is given by psi evaluates at n13 and n24. And this is a Fourier coefficients of pi associated to the unipotent orbits given by 3 square 1. In other words, this integral must be non-zero, so that will give you the proof of the theorem in this particular case. Okay, so I was use the remaining time to state the local theorem. So in this case, we have to replace the global global tool of Fourier coefficients by Jacquet module. So in this case, we can show that if pi is irreducible admissible representation of SO2n plus 1, and suppose there is an irreducible representation of SO2k plus 2l plus 2, actually 2n plus 2l plus 2, such that the Helm space from theta to pi tensor with theta pi is non-zero. And if we further assume that the Twistor-Jacquet module of theta pi with respect to the unipotent orbits O prime that was same as the earlier one is non-zero, then the Twistor-Jacquet module pi with respect to the unipotent orbit O is going to be non-zero. So this is a parallel statement to the global one. So the non-zero integral is replaced by a non-zero Helm space, and the Fourier coefficient, non-zero Fourier coefficient is going to be replaced by a non-zero Twistor-Jacquet module. And other than that, things are basically the same. All right, so I will finish my talk here, and thank you for listening.
Let me thank you, Yusheng, on behalf of everyone. Thanks for the talk. Yeah.
Thank you.
Let me check if any question from the audience.
Yep.
Jialiang or Jinfeng, do you have any question?
Can I ask a question, Yusheng?
Yep.
Okay,
Yep.
very nice talk. So I'm wondering that for this generalized data correspondence, is there a interpretation in terms of long length functionality like we can?
Yes, indeed. So let me go back to the very beginning. So in fact, this lifting respect to the long length functionality in the sense that you can define the dual group of the covers of these special orthogonal groups depending on the degree of the cover. So 2n plus 1, the dual of it is going to be depending on I think depends on the this is even if the degree is even, all right. So this degree is odd. So which means in the even case, this and for the even orthogonal groups, this is it is just itself over the complex numbers. So in this case, this lifting should be respecting the embedding of the group of SO2n plus 1. I mean SO2n plus 1 into SO2. I mean some even orthogonal groups.
Right. Okay. So which means that but is this like for example for this dual group local, do we have this local long length correspondence for this?
Yes, I think this is like both I mean this is like both applies to local and global. Yeah.
So we already have this locally local long length and globally is others multi-formula for this things already proved or still not done?
I'm not sure if the correspondence. I don't think the correspondence is proved in general. Yeah.
Okay.
Yeah.
Okay. And also another.
Yeah. Sure. Yeah.
So another question is because we know in the classical data lifting we have kind of the I think the Rallis or Yamana that result on characterizing this non-vanish of the data lift in terms of local non-variation together with L function criterion non-variation function. So in these cases, do we have this kind of similar?
So that's not in general the case for the covers, since the problem is there's no like a direct relation in the global local connections. So for example, like I mean I don't think that's like no one like alpha. I mean like give you like there's no one like properties you can use in the like I mean like Euclidean properties like for global integrals like this. So I don't know if like this can be done or not, but to my knowledge, I don't know anything that
you mean the global integral is not Euclidean? You cannot write that.
I mean, I'm not sure if it's like Euclidean or not, but it's like there's like no known results that seems to give you the results already. Yeah.
Okay. Thank you.
Yeah. So.
Okay. So Zhaliang, any further question?
No.
Okay, yeah. Thanks again, Yusheng. Thanks for the talk.
Okay, thank you.
Thank
I'll
you.
stop the recording. Thank you.
Okay, yeah. Let me stop the recording.